afternoon. Thank you for coming to this rendition of the KITP Innovate seminar with NSBP. So I'm going to introduce our speaker for today. So we have Morgan Cole. Morgan is a second-year PhD student in physics at Yale University, focusing on experimental astrophysics and instrumentation. She earned her bachelor's degree in physics from UC Berkeley in 2023, with minors in astrophysics and STEM education. Morgan has interned at the Simons Foundation Center for Computational Astrophysics, CERN, and Lawrence Berkeley National Laboratory. She has also been a member of NSBP since 2020 and previously served on the NSBP Student Council. And I can attest that Morgan's great to work with and is great at science communication. So let us listen to her talk now on advancing radio telescope calibration with drones. Take it away.
All right, thank you, Alan. That was a very nice intro. So hi everybody. My name is Morgan. I'm at Yale, like Alan said, and I am in Laura Newberg's lab, if anybody knows it. And I will be talking about my work with radio telescope calibration. I put drones here as like a secondary title because while drones are super fun, unique, interesting, definitely a part of what we do, they kind of take the cake. They become the star of the show. And while drones are great, they're definitely not the main thing I spend my time thinking about. So I will be talking about drones, especially towards the end. But first, I'm kind of going to give a very basic crash course intro into cosmology, or a refresher probably for a lot of you. And then I'll dive into radio telescopes and then my specific role and what it has to do with drones. So, and yeah, feel free to stop me. I think will there be questions in the chat, Alan? Either during the talk or just at the end?
We'll save it for the end, so
Okay.
I will collect them at the end. Yes, sir.
Okay, great. All right. All right. Okay, so just a very brief overview of the history of our universe. Some of you are probably pretty familiar with this. Some of you might not think about this very often in your day-to-day physics life. So just to go over it, in these first few epochs of the universe, you are getting the development of the first particles, eventually the first nuclei, and then they call this period here the first light. I think it's a little bit deceptive because the light that we're referring to here, which is the radiation from the Big Bang or the cosmic microwave background, the CMB, those photons were there all along. But this is the first time where they were able to stream freely through the universe. And that was because the universe had finally stabilized enough to allow for electrons to bond with nuclei, forming the first atoms, the simplest and most abundant atom being hydrogen. So after this period, this is the first period where we're able to detect the cosmic microwave background, the CMB, the first light we are able to measure. So then over the next several hundred million years, you get the development of stars, galaxies, and dark matter. And then they call this period 10 billion years post Big Bang just dark energy. Again, a little deceptive. Dark energy was there the whole time, and it was influencing the evolution of the universe the whole time. But this is the period where dark energy becomes the dominant influence in our universe's evolution. So that's what you see with this like flare out bell shape of this diagram that refers to the period where the expansion rate of our universe began accelerating. And of course, that's the universe we have today, 13.8 billion years post Big Bang. We are in an accelerating expansion universe. Okay, so I'm just going to highlight some of the key epochs here. There's so much to be said about everything I just went over in that diagram. But I'm just going to highlight the parts that are key to motivating radio astronomy and what we're doing with that today. So in these first three periods, we're going to talk about very briefly baryon acoustic oscillations. The key thing to take away from BAOs is the idea that these are sound waves that started in the very early universe as a result of photons exerting pressure on baryons, which are, in this case, you could think of just protons and neutrons. So they're exerting pressure on those protons and neutrons, causing them to first concentrate in these really small regions and then propagate outward in wave-like patterns when the pressure was too great. So the photons were the driving force of those sound waves, But after the first light period, when electrons were no longer causing those photons to scatter and containing them, the photons were free to go, and they essentially stopped driving the propagation of those sound waves, and these ring-like patterns had been created out of the baryonic matter, and they were essentially frozen. There was nothing driving the propagation of those waves anymore. Again, you can think of these as like ripples on a pond. So something in the middle causing that radiation to spread outwards, and then essentially those waves getting frozen because there's nothing driving them anymore. And this is really important for us because we get an idea of what the structure of matter was like in the very early universe. And so by looking at what we have now and sort of retracing that evolution, we know that any changes in these sort of frozen in wave-like patterns were due to the expansion of the universe itself, because there was nothing else interfering with these patterns in the matter. So BAOs are a really useful tool to retracing the evolution of our universe, seeing how its size has changed over time, and have been used in a lot of really important experiments. So that's kind of the key takeaway there. And you'll find a lot in cosmology. I found a lot. The pattern you'll see are that we make use of two of our very powerful resources a lot: how it started and how it's going. How it started meaning the very early data we can get, such as the CMB, the oldest light in the universe, which we can get a lot of information from of the universe's structure and its evolution patterns. And then we can compare that to what we see today. So you can think about Hubble and JWST, looking out at the sky and seeing what the universe actually looks like. So if we want to explain our universe, its evolution, have a model to understand what's going on, you essentially want to be able to connect these two dots, right? Have a model that can explain how it started, that also can explain how it's going right now, what our universe looks like today. Easy enough, right? And actually, surprisingly to me at least, this model, the lambda CDM model, to me is a relatively simple, can be explained relatively simply, and has been extremely successful in describing our universe very accurately. So lambda refers to dark matter, the energy density of dark matter specifically, and CDM is cold dark matter. So that's just the specific form of dark matter that we're assuming in this model. Again, just to highlight what's relevant for us today, we can see from this diagram, this is describing basically the evolution of energy density of the different components of our universe as the size of the universe has changed, which you could think of as over time. So the three things we're looking at here are matter, radiation, and lambda, which I said is dark energy. So we see that matter and radiation on a logarithmic scale have these decreasing patterns. So the energy density has decreased of radiation and matter over time, and dark energy has remained constant in this model. We're assuming the energy density of dark energy is perfectly constant, has been since the Big Bang, and depends on the Hubble constant, as this equation shows, A being the scale factor. So you can see this period right here is where the crossover happened, where dark energy began to dominate our universe, become the dominant component, and that leads us to where we are today. So this model, again, the key thing to take away, if nothing else, about the lambda CDM model is that lambda, being dark energy, is assumed to have constant energy density throughout the universe's history. And like I said, this has been an extremely successful model in explaining our universe's evolution, in giving a good picture that matches what we see today. And people are very happy with the lambda CDM model, but it is a little bit imperfect. There are some things it does not exactly explain, some things that the model would predict that don't totally match what we're seeing today. We call those tensions in cosmology and astrophysics. So the first one I want to highlight is the Hubble tension. Some of you might be familiar with this concept. So the Hubble tension is referring to measurements that have been made or predictions that have been made about the Hubble constant, which is important in describing sort of evolution rate of our universe. And like I said, those two methods of exploring things, how it started and how it's going. How it started in this case would be the CMB measurements. So looking at the CMB, the oldest light of our universe, and using it to sort of determine what the evolution rate of our universe should be is one method. And the other is the local distance ladder method. That basically refers to actually looking out at the night sky today, measuring different objects in our universe, like Cepheid variables, for example, and using those and their known distance and brightness to make a direct measurement of how much our universe is expanding, how quickly things are moving away from us. And as you can see, those two models come up with a value of, 70-ish for the Hubble constant. And over time, over publication years, those measurements have gotten more and more precise. Those error bars are shrinking, yet they are disagreeing more and more. So in the early 2000s, it seemed like those two measurements agreed at least well enough within some error. But as measurements have gotten better, it's more and more clear that what the CMB model predicts and what we see today using the lambda CDM model, those don't exactly match. And so that's very interesting, and for some people, a little bit concerning, pretty concerning. And people want to understand why that would be. We do not yet have an answer to that. And another maybe lesser known tension that I also don't claim to understand super well is the S8 tension, the sigma 8 tension, which, to put it very simply, refers to the idea that the lambda CDM model, using our early measurements to predict what we should see today, expects that the distribution of stuff in our universe, again, galaxies, stars, etc., should have a certain level of, you could say, clumpiness. So stuff should be sort of gathered, squished together a certain amount or spread apart a certain amount. The lambda CDM model predicts it's about, we'll just say, this clumpy. And DES refers to dark energy survey. Actual measurements have showed that it's actually a lot less clumpy than this model would predict. The stuff in the universe is distributed a lot more smoothly than we would expect based on the lambda CDM model. And we don't have an explanation for that either. And so people are very interested in these tensions because they are, of course, making us want to look a little bit more closely at the lambda CDM model. And so, like I said, I'm bringing back to the idea how it started, how it's going. Basically, people are trying to connect these two dots, right? They're trying to jump from the first light using the CMB measurements, the oldest data we can really get, to jump to try to explain what we're seeing today. And when those two things aren't exactly matching, people are naturally curious about maybe we should look a little bit closer at what's going on here in these in-between epochs. And so that's what some more recent experiments, such as the ones I work on, are more interested in, is, well, hold on, let's make sure that we know what's going on here and see if that aligns with our models. And if it doesn't, then we have more interesting questions to look at. So one of those main experiments that have embarked on that endeavor and come up with some very interesting results is DESI. Some of you might have heard of DESI, the Dark Energy Spectroscopic Instrument. So DESI is looking at this period based on redshift that is about 1.5 billion years after the Big Bang. So this is long after the first light, the 380,000 years, and certainly pretty far in the past from today. So it's looking at that in-between period. And what it's doing is looking for those baryon acoustic oscillations via galaxies. So when we, going back to the diagram I showed of those BAOs, those little rings with the dots in the middle, that's obviously not what you see when you look at the night sky. You see scattered random stuff everywhere. So those patterns are inferred through statistical analysis. You basically look out at the night sky, you see where stuff is, you find sources, and you do your statistical analysis on where you're more likely to find them versus less likely to find them. And that's how you infer the structure of BAOs. And by looking at epochs in the past from older redshifts, you can see how that's looked over time. So what DESI does is it specifically looks for galaxies, as many galaxies as possible in galactic surveys, and tries to understand and analyze their position and how it's changed over time. And so what they have found by doing that, by tracing out the evolution of the universe using the BAO patterns and galaxies, is that dark energy might be a little bit weaker than we thought and maybe more shockingly, dynamic, as in not constant. So if we go back to our model I showed before, we might now think that the true lambda CDM model looks more like this, has this sort of error bar uncertainty region around what we assume the value of the energy density of dark energy to be. And we expect it, results have been consistent with seeing that it might be a little bit weaker than previously predicted. If you remember on the previous slide, this value, this is just a proportionality constant, was 1. Now we're thinking it's maybe minus 0.99 plus or minus 0.13. So that might seem like a very small difference, but there's a big difference between perfectly constant and dynamic. And so this is a very recent result. People are very intrigued by this. So of course, people are looking to look into this even more, confirm these results with other experiments, and then ask, of course, what does that mean? What does that mean for our model of the universe? So, while DESI's method of galactic surveys is very effective, it is not necessarily the most efficient because it requires you to find and resolve individual sources, the galaxies, and finding as many as possible in order to be able to make any kind of claims about statistical patterns. That takes a long time. That takes a lot of effort. And so, what another method people are looking at is hydrogen intensity mapping. So as I said before, and as you might already know, hydrogen is extremely abundant in our universe. It's the simplest atom, and it has been around for a really long time. And so it is pretty much everywhere. And if you're able to then map hydrogen and where it is, how it's distributed throughout our universe, you can also get a really good idea on how our universe has evolved throughout its history. And so that is a method people are looking into. Again, like I said, you measure hydrogen density, which means you don't need to resolve individual sources. You don't need to look for individual galaxies. And it can be a little bit more efficient than mapping galaxies. And so what do you actually measure? You can't just like look and take a picture of hydrogen. You're actually measuring the 21 centimeter photon that hydrogen emits during its hyperfine or spin flip transition. So this kind of calls back to maybe your early quantum classes or maybe even high school chemistry classes, where you know that atoms emit their characteristic frequency of light. And because it is always 21 centimeters during this transition, it is very easy to reliably detect this signal or look for previous redshifted versions of this signal. And because hydrogen has been around for a long time, you can get a pretty complete history of our universe by looking at hydrogen's distribution. And yeah, so pretty much neutral hydrogen has been abundant since the recombination period, which was that 380,000 year post Big Bang era. And so it's extremely useful. Okay, so before I'm about to jump into my actual research, what I sort of do on a daily basis. I'm just going to give a little recap of the things I've said so far. Again, that was maybe just a quick refresher for some of you if that was familiar. If not, that might have been a pretty big info dump. So the key takeaways, just moving forward, if you don't remember anything else, that's okay. Number one is that dark energy is very mysterious. There's a lot we don't understand about it. The lambda CDM model has made some very nice but not entirely complete predictions of dark energy and its evolution. Our next main point is that we might need to be looking at some more recent eras of cosmic history, those intermediate periods, to try to understand what might be going on to check our models. And finally, that 21 centimeter photons emitted by neutral hydrogen might be the key tool to help us detect cosmic evolution, to be able to get a close look at the influence of dark energy throughout our universe's history. All right. So, pivoting a little bit, I want to talk about this model that I have thought about a lot over the past year or so, the model of the upside down wedding cake. So this is where we start to get into drones a little bit. So in order to, if some of you might know this, if you've done anything with drones recreationally or for research, in order to have a drone, to fly a drone in the United States, you need to have an airman's license. So you need to literally go take a written exam. It's not an easy exam either, in order to get your drone license. And you need to learn basically like basic airman law. It's very similar to the exam you would take if you're trying to become a pilot. And so I learned a lot about stuff that I never thought about before. One of them being restricted airspace, places you cannot fly. Not that I ever think I will be flying near airports or anything like that. You still have to know that for the exam. This is the model that they would show when they're describing restricted airspace around an airport. So if this is the ground and here's your airport right here, this is like the no flying zone, and then this is as you go higher up, the region that you're not allowed to fly in gets a little bit bigger. So they say it's the upside down wedding cake. Now, I've been thinking about this model a lot for some reason. I think I have found it to be a very good analogy for sort of thinking about the context surrounding my research. I think it's apt because this like bottom tier, like that's the foundation of everything I do, but it's also kind of the smallest part of what I spend most of my time thinking about and studying. So for me, that base layer is cosmology and radio astronomy itself, kind of everything I just talked about. Yes, it's the foundation of what I do. It's super important, but it's not really what I spend my day-to-day thinking about. A little bit closer to what I actually do are thinking about radio telescopes. Radio telescopes, of course, the whole goal is to figure out new things for cosmology and radio astronomy, but I focus more on their specific properties and capabilities. And finally, the top of the wedding cake, if I am up here, is thinking about the drone-based methods for calibrating those radio telescopes, which are used to study cosmology. So this is sort of the whole context surrounding my research. I've talked about this stuff so far, so I'm going to keep my little wedding cake in the top corner of my slide for the next couple of slides, as sort of a reminder for where we are and what we're talking about. So you see it up there. I have it blocked on Zoom. Yes. So to say a little bit about radio telescopes themselves, first I'm going to just go over the key two experiments. These are hydrogen intensity mapping experiments, which I'll be focusing on for the majority of my PhD. We have CHIME and we have HIRAX. So you might see from these pictures, they look pretty different, but CHIME and HIRAX are actually intended to be sister experiments. So they have the same goal, which is to measure in the 400 to 800 megahertz bandwidth. And that, in terms of redshift, corresponds to 6.5 to 10.5 billion years after the Big Bang. They are both interferometers. As you can see, there's a number of different dishes in each of them that combine to form one composite image. They have a large field of view, so they look at a lot of the sky at once. And CHIME is in Canada, so it's in the northern hemisphere. And HIRAX is in South Africa, so it's looking at the southern hemisphere. So they cover large fields of view in both hemispheres. And the goal overall is to create those hydrogen density maps to essentially get a nice map of the density distribution of hydrogen as we can see it. And from that, by looking at it through previous historical epochs, we can infer how dark energy has influenced the structure of our universe, specifically through the ring-like patterns of baryon acoustic oscillations. So, very ambitious goal. That's what we're going to be looking at. And so something that is really key to note is that you have to have very precise measurements because the influence of dark energy is very slight, relatively small. So you need to have really high precision in order to be able to claim you've made any substantial measurement of its influence. And that's kind of inherently difficult when you have a large field of view. It's hard to be precise, but also have a large field of view and take these like big sweeping maps. So what that means is it's really important that we calibrate our instruments as well as possible so we can get the best possible understanding of our data and make the strongest claims in our papers. Okay, so still talking a little bit about radio telescopes. I think a lot of people sometimes get hung up on the idea of a radio telescope because it's not necessarily our traditional telescope with a nice little lens that you can look at the sky through. It looks like an antenna. It is an antenna dish, so you're receiving radio signals. So what does it mean to calibrate something like that? Essentially, you can think of the key thing we want to know is the shape of our beam. And you can think of that as analogous to the lens of a camera. So every camera or every telescope has a characteristic lens shape that changes slightly the way things really are in the measurements you make. So if you have like a fisheye lens, if your scene looks like this, what you're actually going to measure would look something like this. But if you know what the world normally looks like, you can understand, okay, this lens is manipulating the world, the image, to look a little bit more like this. But of course, if we're looking at unknown sources, we don't know what it's actually supposed to look like. We don't know what distortion is because of the shape of our lens or is what things actually are. So it's really important that we understand the beam shape that we have with our radio telescopes. And so, yeah, to kind of go over the key things that I just said there, if you want to figure out what kind of lens you have with, let's say, a camera and how your light is being distorted in your images, well, you would find a known reference, something you could take a picture of something that you know what it's supposed to look like because you've seen it before, you've measured it a million times, you know what the image should look like. You could take a picture of it, and then you compare the picture you took to reality. And you know that any difference is because of the shape of your camera, the shape of your camera's lens. So, simple enough. If you want to retrieve your original image or get a most accurate image of what your picture should really look like, then you want to subtract those differences out of those images. Okay, and so that is essentially what we are doing when we're calibrating our radio telescopes. So our known source in this case could be a star, it could be a galaxy that has been measured and studied very well. We know what you're supposed to measure. You point your radio telescope at it, and then you might want to move it around to be able to see it from different angles, because maybe the edge of your lens distorts things differently than if it was taken right at the center. You want to get a full understanding of what you're looking at. And then you would extract some kind of map like this. So this is a very simple example of what a beam pattern might look like. So you'd see your highest gain at your center position, and then you might see some features like these side lobes out to the side as you rotate your antenna side to side. And this would be, you could say, okay, now anytime I look at anything in the sky, I know that this is the sort of shape of my lens, the shape of my beam pattern. So that is all well and good, except if you cannot move your telescope. It gets a little hard to make a map like this at different positions because it can't be rotated. And this is a HIRAX telescope, and it's the same with CHIME, the two experiments I work on. You can't rotate them. They have no moving parts. So sure, you could wait for them to be aligned with some celestial source, but you don't have control over being able to look at the different features of it anytime that you want. So that's kind of a major restriction in calibrating these sort of instruments. So what can you do? Well, instead of just hoping for some source out in the sky, you can create one. You can essentially introduce a radio signal in the sky that you can control the position of, and that is, of course, where drones come into the picture. So this is an image of our actual drone with our actual radio source attached. It is sending a radio signal that this dish can receive. And because it is a drone, you fly with a nice little remote controller, you can go tell it exactly where to go, exactly where to be, and you can measure all the different features of your telescope or your radio telescope and get this beam pattern, which, like I said, is the key to calibration, is understanding its beam pattern. All right. So in reality, you want a more comprehensive beam pattern to fly a nice grid over your telescope. And this is an example of what our beam maps will normally look like. Once we've obtained a calibration map, you'll be seeing something like this. And so it sounds relatively simple. So how is it going to be a whole PhD? Well, it's not as simple as it sounds. There's a lot of complications and things we need to be very sure about in order to make those kinds of claims. Number one is that you have a distinct, well-behaved, and well-understood radio source. So the thing that's sending the light signal into the dish, you have to make sure you know exactly what it's doing at all times, because that's like comparing it to reality, knowing what you're supposed to measure. And so for us, that is a device like this. This is what we call our analog noise source. It has a GPS clock, all these other components. It's battery powered, and it goes on the drone in this little box, which we can control with these switches. And then this fancy blue thing is the antenna that broadcasts the radio signal. A second thing that you need to be sure of is that you have very highly accurate position data coming from your drone. So you need to know exactly where your drone was at all times as you're flying over the dish in order to say, all right, this is what this part of the dish looks like versus this part. And so in order to do that, we have this fancy drone that comes with this, it's called an RTK. It's essentially a reference antenna that we put out in the field when we do these flights that talks to the drone as it's flying to help it have a steady position. And this fancy drone saves its GPS position markers to this controller at all times. So you can fly the drone around and then you can upload a file from this controller and it will tell you exactly the pattern the drone flew in. It'll show you a nice map of it. You can get the longitude, latitude coordinates from any point in the flight. It's really cool. It's really fun to use that tool, honestly. And the last major thing I think you need is to have a secondary reference to compare to constrain your time delays. So this part is a little bit subtle, but basically, if you are just using one receiver antenna to measure the drone, you can't really compare it to anything to make sure you have a secondary check. So what we do is we have one signal sending source. This is a board that sends radio signals that goes on the drone, and another one that does not, that stays on the ground. And they are both getting measured by the same device. So this flies up in the sky on the drone and will get measured by our antenna dish. This one stays perfectly stationary. So we compare what's measured on each of those, and they're perfectly synchronized. They should be sending the exact same signals at the exact same time because they're GPS locked. And by comparing them, you know any difference was due to interference in the sky, the drone's position, etc. So you can then subtract that out. And that's really important to be able to claim that we made any reasonable measurement with our drone. Okay, so this is kind of a recap of those things that I just talked about. The primary challenges are constraining those errors and really optimizing your radio noise source. Another thing that I haven't really mentioned that I could go into a little bit later is the idea that the far field of your telescope, which is the part that sees space, sees deep sky, is often way too high, actually, for a drone to be able to reach. So if you want to make good drone measurements of the sky and be able to say our drone is imitating what you would see if you were measuring space, you can't always get that high, either legally or physically. You're not able to get the drone that high. So we might need to come up with a method of flying a little bit lower and then inferring what we would see if we looked further away. And there's always logistical constraints, right? There's only so long. The drone can only stay in the air for about half an hour to 40 minutes with nothing on it, and then we attach a bunch of heavy, obnoxious stuff to it, and it gets upset, so it can really only fly for about 20 minutes. So that's something else that is actually a major constraint we have to take into consideration. And it can only, we can't charge it while it's up in the sky. So we're constrained by a number of obstacles we have to think about. So some recent things that we've done to address some of those issues, that part I talked about where we have a secondary source, one that goes on the drone, one that stays on the ground. That method had not previously been validated until a few months ago when my team was able to pull that off and get some very nice results that we hope we're going to be able to publish soon. That significantly enhanced the smoothness of our measured beam map. So it showed that you can subtract out a lot of noise, get a more accurate measurement, and have nicely synchronized signals with two separate references. And so that's a measurement we're actually going to repeat, I think, sometime next week and have some results coming out about that pretty soon. So that's really exciting. And another thing I'm going to be working on, like I mentioned, sometimes you can't fly the drone as high as you need to. So you might want to try measuring a little bit closer to the dish and then using maybe a machine learning algorithm to infer what the signal would look like if you had flown higher. That would open up a lot of possibilities for being able to fly in different environments that we have not been able to fly in before. And so that's something I'll be working on over the next probably couple years. That's already been started by members of our team. And yeah, pretty soon I will need to eventually put this into practice. Lately, we've just been testing it on this little 3-meter dish that's in Yale's backyard. But ultimately, we want to take this to major experiments such as Hyrax in South Africa. And another collaboration we have is with the Green Bank Observatory, which is in West Virginia. It's gorgeous. It's in the middle of nowhere. Radio experiments tend to be in the middle of nowhere, which makes field work pretty interesting. So those are some things that I have coming up, some trips around the world. And yeah, here's my team. I will take questions after this, but I just want to introduce the people on my team. This is Ella, Mallory, and Kalyani, and they have been super helpful. They're very smart in helping me do this work. So, yeah, I think that's pretty much all, and I will take questions now.
All right, thanks so much, Morgan. That was a really good talk. So yeah, we will take questions in the chat. I'll be observing for those. And I
Great.
guess to top it off, so we're not waiting, I had a question. So in the event that you made maybe sturdier drones in the future,
Mm-hmm.
and um you get to a place where you can legally and feasibly go higher,
Yes.
what is the range of like the radio signal that your drones can emit? I understand like the whatever observatories you're using are probably sensitive, but
Right.
yeah.
No, that's a really good question. So actually the problem we're having now is that our radio sources tend to be way too bright for how close we're flying. Obviously the signals well, maybe not obviously. The signals we're measuring from deep space can be really faint. And so we actually would like the drone and its signal to be a little bit closer to that. So I'm not exactly sure how high would be too high, but feels like the sky's the limit right now. We would actually love to be able to fly a lot higher to be able to have that signal be more easily within our range. Um, and so I don't know if I could give you a value of like how many meters, above sea level would be too much for us. But we're nowhere near that limit yet, is what I can say. Of
All right. Yeah, awesome. Thanks for that explanation.
course.
Um, anyone else in the chat? Okay, we got somebody in the Q&A. So Nia Sweet says, "Thank you for sharing your research on this interesting topic. Drones are very cool, but as you mentioned, have a limit. Have you considered trying out high altitude balloons or statistics that can make it to the stratosphere?"
Yeah, that's a great question. So I personally have not worked on stuff like that, but that is definitely stuff that people are doing. People have used high altitude balloons to make these kinds of measurements. And while that's really great, the one drawback is that you don't really have as much control over the position. It's still more control over the position than you would have if you're looking at like a galaxy or a star. You can obviously predict that, but you can't control it. So that is something people work on, and I'm not familiar of anyone who I know personally that's doing that right now. So drones are sort of seen as the next frontier, but I think we might need to do some combination of that in the future if we're trying to work on these really high altitude, high far field telescopes. So that's a great question.
Yeah, for sure. Um, yeah, there's more time for questions, so please put questions in the chat if you have them. Morgan, I'll probably also ask, I guess with regards to the future of using drones and this technique for calibration,
Hmm.
um, is this the cutting edge and the kind of like the standard of the industry, right? Well, the scientific field right now in terms of calibration, or are there other technologies that they want to start using soon?
Yeah, from my understanding, I mean, a lot of the methods of radio telescope calibration are relatively new because radio astronomy is a relatively young field. And so, from my understanding, drones are sort of the newest cutting edge, completely different development, especially some of the stuff we're doing with digital noise source, those like separate synchronized boards. That's not anything anyone has done so far, and if it can be done, I think is probably one of the more efficient, um, trusted methods to be able to do that. Um, I'm not super familiar with any very new developed methods, but other things people have done are similar to this with just other radio noise sources that you can put like a far distance away from your instrument. There was a study done with that on the Hera experiment that I'm familiar with. But again, the key difference, and I think the reason we are particularly so interested in this, is that we do not have moving parts on our telescopes. So there's a lot you can do and a lot of new stuff being done, to my understanding, for telescopes that have moving parts that can be more efficient, but there's not a lot of other new solutions I'm familiar with for stable or fixed position devices. So yeah, this is something people are really interested in.
Yeah, that makes sense. Thank you.
Hmm.
Um, hmm. Any more questions in the chat from Morgan? We have a little bit of time left. I guess while we're okay, there's another question. Here we go. Ben K asks, that was an amazing talk. While I was at Green Bank Observatory, they had several restrictions on electronic devices in the area due to noise. Have you been able to account for the noise coming from the drone and controller and remove it from the observed signal? If yes, how was this achieved?
That's a really good question. So I personally have not been to Green Bank yet, but members of my team had, like right before I started here, and had done flights out there. Yeah, that's a very good point because that was an issue that they were having. If you remember, I mentioned that RTK, the like stationary reference antenna that comes with the drone. There were a lot of problems in getting that to talk to the drone, and I think they ended up just not using it. It's a little bit of a trade-off for the position stability of the drone. But I've had that problem even just here at Yale. Obviously, we're not in any kind of radio quiet remote area here in New Haven. But even like passing cars in their radio can interfere with the drone and RTK communication. The good thing is that you can know the frequency that the drone and the remote controller and all that are communicating. I want to say it's like 2.4 gigahertz. It's the Wi-Fi frequencies. And I think you could even change it if you wanted to. So the good thing is you know where it's supposed to be, and you can always fly the drone with no radio source on it and see what measurements you make as a baseline for your noise measurement. But the good thing is, as I showed before, we are mainly concerned with the like 400 to 800 megahertz bandwidth, which is nowhere near the Wi-Fi communication frequency. But it definitely is an issue that we have to think about and has caused problems before. So that's a really good question.
Yes, thank you for that question. Um, I guess before we sign off here, do you see yourself kind of more concerned with these new developments with dark energy and understanding maybe if it's dynamic or not? Or do you see yourself more as somebody who is going to specialize in the instrumentation side of things that we can understand dark energy?
Yeah, no, that's a great question. I mean, yeah, thinking back to my upside down wedding cake, definitely I'm super interested in cosmology, and it's always nice for me to remind myself of the like broader context that's going on. Actually, just a couple weeks ago, I got to meet Wendy Friedman, who, if you don't know, is one of the key players in the Hubble tension discussion, and got to talk to her about these issues and what she thinks and the stuff that I'm doing. And so it's always really nice to have that in the back of my mind, and it's I think good for me to know there's a broader goal that is really interesting to me. Of course, I don't really think about that on the daily. I think about the instrumentation side, like you said. But I think I like to be sort of somewhere in between for my own personal preferences. I think it'd be harder for me to be invested even in the instrumentation side if I wasn't interested in the broader cosmology question that it was working towards. So, yeah, it's a great question.
Right, that makes sense. That makes sense. All right, so if there's no more questions, we definitely are grateful to have had you give this talk, and
Thank you for
thank
having
you.
me.
Yeah, for sure. And everybody, thank you for attending this talk, and we will see you in the next iteration of the NSBP KITP Innovate talks. So thank you, and have a good day.